What would happen if we were to take a powerful telescope and keep it fixed at a small area of the sky where there doesn't seem to be any stars? Would we see anything really far away? That was the idea behind the Hubble Deep Field image. They picked a spot close to the Big Dipper. Zooming into that spot, they picked this smaller area in which there doesn't seem to be any star. Over 10 days with the Hubble Space Telescope, they took 342 separate exposures of this small area. And the result is the Hubble Deep Field. Pretty much every speck of light in this image is a galaxy. There are about 3,000 galaxies in this image. And the area of the sky covered by this image is only 1/24 millionth of the whole sky. So if space looks like this in every direction, we should have 3,000 galaxies times 24 million, about 72 billion galaxies in the universe. This is just a rough estimate. Does space look like this in every direction? A few years later, the Hubble Deep Field South was taken. This is a region in the constellation Tucana that also seemed to not have any stars. But over 10 days of exposure time, we were able to detect many galaxies. A few years later, in 2004, the Hubble Ultra Deep Field was taken in the constellation Fornax. And then in that same region of space, a newer picture was taken in 2012, the Hubble Extreme Deep Field. The homogeneity and isotropy of the universe on large scales, in other words, that it looks roughly the same in any direction, are two major components of the cosmological principle, one of the two principles on which our current best understanding of the universe lies. The other principle is that the laws of physics can be applied anywhere in the universe. Cosmology is the study of the cosmos as a whole. Cosmos comes from the Greek word for order or orderly arrangement. For the past 100 years or so, after Einstein's general relativity, we've been able to study the origin, evolution, and eventual fate of our universe. And this is scientific or physical cosmology. For millennia, there have also been religious cosmologies. The Genesis creation accounts, for example, are a religious cosmology, and we discussed those in a previous lecture. Creatio ex nihilo, the doctrine that God created the whole universe out of nothing, is not contradicted by anything that's been studied in scientific cosmology. But when we do want to connect religious cosmologies with scientific cosmology, philosophy has a role there. We have to use reason to understand the nature of space and time, the difference between being and non-being, also the nature of science, especially physics, and religion. And so philosophy is where this dialogue between scientific cosmology and religious cosmology takes place. Because we're in a course on astronomy, we want to focus on scientific cosmology, but without ignoring the points of contact with philosophy and religion. The Big Bang model is our best scientific explanation based on physics and observational astronomy. We've already discussed in a previous lecture how scientific cosmology was made possible due to Einstein's theory of general relativity, how Edwin Hubble discovered that the majority of galaxies are receding from us, how Father Georges Lemaitre thus reasoned that in the past the universe was smaller, and if we go back far enough, we can go all the way back to a primeval atom, as he called it. How this became known as the Big Bang Theory. How Penzias and Wilson in 1964 stumbled upon the cosmic microwave background radiation. and how we've recently measured and mapped the anisotropies of the cosmic microwave background. The Big Bang model has been refined over time as new discoveries have been made. So based on today's Big Bang model, how has the universe evolved over time? We begin with an initial singularity, and the singularity, in fact, cannot be described by general relativity. The most popular theory for what happened next is inflation. The universe started out being filled with extremely high density, pressure, and temperature, and it was rapidly expanding and cooling. At approximately 10 to the negative 37 seconds after the beginning, there may have been a sudden inflation of the universe, faster than the speed of light, so that temperatures dropped by a factor of 100,000 by the time inflation ended, around 10 to the minus 33 seconds after the beginning. During inflation, the universe's volume would have increased by a factor of 10 to the 78. A plasma of quarks and gluons was produced, and there was a small excess of quarks and leptons over antiquarks and antileptons. Quarks and gluons combined to form baryons, such as protons and neutrons. This is called baryogenesis. The mystery that there was slightly more matter than antimatter resulted in the fact that we now have matter today. After the annihilation of antimatter, the remaining baryons and leptons were no longer traveling at relativistic speeds, so the energy density of the universe was then dominated by photons. This is reminiscent of the fiat lux, let there be light, but we shouldn't be hasty to make parallels in case the scientific model changes. A few minutes after the beginning, some protons and neutrons combined to form helium and deuterium. This is known as the Big Bang nucleosynthesis. The universe continued to expand and cool, and after about 379,000 years, the energy density was low enough to favor recombination of electrons with protons and hydrogen atoms. Due to recombination, photons could then travel freely through space, and we detect these photons as the cosmic microwave background radiation. We had to use extremely fine-scaled instruments to detect any anisotropies in the cosmic microwave background. But those slightly more dense regions would have been the first regions to accumulate matter and grow into structures. The first stars formed about 400 million years after the beginning, thus ending the Dark Ages. Over time, these stars accumulated into galaxies, and also around those stars, planets were formed. The expansion of the universe was at first slowing down as matter pulled on itself through gravity. But more recently, the expansion of the universe has been speeding up as the result of dark energy. It seems that the universe is about 13.8 billion years old. That last digit fluctuates a little every few years due to new evidence. But what is dark energy, and what could it mean for the future of the universe? We don't know what dark energy is. We just know that the universe is accelerating in its expansion, and this physical effect should have a physical cause. How do we know that the universe is accelerating in its expansion? We know this from measuring the redshifts of type 1a supernovae. Because the certain type of supernova releases the same amount of energy whenever it happens, we can look at how bright those are and know how far away they are and how fast they're moving away from us. So it's possible that dark energy doesn't actually exist, and that a theory that improves upon general relativity can do away with the need to invoke it. But for now, it still seems that a universe with dark energy is more likely to be the case. In the past, at the time of the cosmic microwave background radiation, when the universe was about 380,000 years old, it would have been dominated by dark matter. But today, dark energy has taken over and now makes up about 70% of the density of the universe. Assuming the density of dark energy is uniform across all space, that is, that dark energy is a cosmological constant, then it's about the density of 7 times 10 to the minus 30 grams per cubic centimeter. An alternate proposal is that the energy density of dark energy varies with space and time. The fate of the universe depends on the nature of dark energy and on the shape of the universe. We don't really know for sure whether the universe is flat, like Euclidean space, closed, like the surface of a sphere, or open, like the surface of a saddle. If it is closed, then gravity will eventually stop the universe's expansion. But if it's flat or open, then maybe gravity will slow down the expansion, but might not be able to halt it, and it could expand forever. The three main hypothetical fates of the universe are the Big Crunch, the Big Freeze, and the Big Rip. The Big Crunch will occur if gravity overcomes the universe's expansion and will cause the universe to contract. An example of the Big Crunch would be shown in this curve that rises and then falls, like when you throw a ball up into the air and then it comes back down to Earth. And this specific curve was made in the plot with a density of matter 6 times the critical density. With exactly critical density of omega m equals 1, the universe would still expand outward forever. And also, if the density of matter is less than 1, between 0 and 1, then it could still expand forever and expand at accelerated rates. If that happens, we call that end the Big Freeze. Sometimes I've also heard the Big Chill, or the heat death of the universe. In this scenario, stars burn out, leaving behind white dwarfs, neutron stars, and black holes. Black holes will grow, but would eventually evaporate. The entropy of the universe would be too high for new structures to form. So the universe expands indefinitely, and that expansion could slow down, but would never stop. Another scenario in which we have dark energy, this omega with subscript lambda, the universe accelerates in its expansion, and perhaps someday dark energy will overcome gravity as well as the other fundamental forces, ripping apart all structures, even atoms. That would be the most violent end of the universe. But all of these scenarios are many billions of years from now. It's certainly the case that God could choose to end the universe anytime sooner. One way or another, this universe will end. So we place our hope beyond this universe. We place our hope in God, who has allowed us to understand our universe, but who also calls us to be with him. So we yearn for truth, and we are excited at all the scientific advancements and all the knowledge it has brought mankind with it. But we also have higher hopes for the next life, the next world, and I hope to see you there.